Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at OneSpin with Sven Beyer, who's going to talk today about how to achieve sufficient coverage in large SoCs.
So Sven, as chips get larger, as they get more complex, what sort of problems are you running into in terms of ensuring that you have sufficient coverage?
Well, first of all, to cope with all the increasing complexity, it has become actually mainstream to use a wider portfolio of tools. It's no longer just the simulation tool that you are running, but pretty much everybody in this space has actually started to integrate formal verification as well. And of course, as soon as you try to put two different tools together, problems arise in terms of both verification planning and also to actually aggregate the coverage again, in order to achieve the coverage goals that you actually have for the full chip.
So Sven, it's not just verification of a static chip, right? You think about automotive, they have a long lifetime. You have to know what the chip is, how it's going to behave throughout its lifetime.
Yeah, sure. And you also have to make sure, all the future revisions that you are going to do and the few parameterizations and later spins that you are doing, actually still keeping up and keep all the track of all the verification you have already done, so you don't really duplicate any work.
So why don't you draw this out for us?
Sure.
So Sven, what are we looking at here?
Well, we are looking at the traditional chip design and verification process, right? You start up with your verification plan, where you collect your requirements and break it down into different features and tests. Of course, then there's your development, where you have your full chip with lots and lots of different subblocks. And then, of course, you do collect coverage for all the chip that you are developing.
So as you get into multi-billion gate designs and you have a lot of different types of chips in there, so you've got GPUs and CPUs and potentially various types of accelerators, does it become harder to verify the interactions between these different chips?
Absolutely. The more different components you add, the more paths you get and the more communication you get. So you essentially add another level of complexity there.
And where does formal fit into that whole picture?
Well, there also formal can help, because also these days some very specific apps have been developed to address designs of that size in order to, for example, look at the connectivity between the different blocks.
As we get into these more advanced chips, you have more functions on there, and those functions have to behave sometimes synchronized in different ways. Where does formal fit into that picture?
Well, essentially, formal still supports, on the one hand, the idea of divide and conquer, right? So look at each of the different functions independently and then kind of integrate them together so that they are properly wired up and properly communicate so that you get back to the full picture.
Another layer on this is all the potential different use cases that get involved here too as well, right?
Sure, yeah. If you look at the different use cases in simulation, right, you might want to kind of trigger them explicitly. You might make sure you cover them and have it somehow executed. Whereas, of course, formal offers the aspect of the exhaustive side, so you do get certain quality results that are independent of use cases.
And really what you're trying to search for there is the anomalies and the bad behavior that you weren't expecting in the initial part of the design, right?
Exactly, and formal, of course, on the one hand has the exhaustive nature, but also some of the specific technologies here also enable you to look for stuff that you have not really been planning for, to make sure that nothing else is actually inside your chip.
Can it also start tracking some of the interactions between hardware and software on a functional basis?
Absolutely. In particular, if you start on the software stack at the lowest level, kind of the system software, there are a couple of approaches also informal to look at the processors together with the system software and make sure actually this layer is behaving as expected.
But it also starts feeding into now the algorithms that are being run on these chips, right? So you think about an AI chip, for example, it has a lot of different blocks and potentially a lot of interactions for the algorithms that you didn't have in the past.
Sure, of course. That adds a lot more complexity to it, right? On the other hand, you have the hardware computation power, right, where you may be able to do some specific arithmetic verification on the formal side. But then for the software layer, I mean, there's also some approaches that we, for example, have to look at, actually read in system C designs and be at that level and actually also do a little bit kind of software style of verification.
Sven Beyer, thanks for a great explanation.
You're welcome, Ed.